Right, law gives a way to find the magnetic field due to elemental current, or say current element. Current element means a small length of conducting wire that carries current. Right, gives the way to find the magnitude and direction of the magnetic field due to that current element. Consider this figure. This is current carrying wire. Here we have considered a small length DL that also carries the same current as the conducting wire. The magnetic field is calculated or given by Weierstrass law at some distance from that current element. The elemental flux density at any point due to that current element is given in magnitude and direction by given in magnitude and direction means in vector form. The elemental flux density is given by dV vector is equal to mu naught upon 4 pi I dl cross r cap upon r square, where that r cap is unit vector along the vector r, and mathematically it is given by vector r divided by its magnitude. So if we substitute this formula, we get this expression in new form as dv vector is equal to mu naught by 4 pi I dl cross r vector upon r cube. As I said, r cap is the unit vector along vector r. Mu naught is the permeability of free space. R vector is the radius vector joining the field point and the source point. Field point is the point where we are calculating magnetic field, and the source point is the point due to which magnetic field is produced. The magnitude of this flux density is given by dV is equal to mu naught by 4 pi I dl sin theta upon r square. You can easily get this formula just after using cross product of two vectors. Say a cross b is equal to ab sin theta. Here dl cross r will be equal to dl r sin theta, where theta is angle between dl vector and r vector. And the direction of this magnetic field is perpendicular to both dl vector and r vector, or say perpendicular to the plane containing both dl vector and r vector. Now let's discuss some applications of Weierstrass law. The first application is the magnetic field at the center of a current carrying circular coil. We can find magnetic field due to different shapes of conductors carrying current using Weierstrass law. One of these is the magnetic field at the center of the circular coil. Here we consider a circular coil of radius small r carrying current I in anticlockwise direction as shown in figure 1 here. To calculate the magnetic field at the center O, consider a small element of length dl at point A, then join O and A such that O is equal to R. The direction of dl is along the tangent at every point on the circle. So dl will always be perpendicular to r vector, hence we take theta is equal to 90 degree. Now the magnetic field at the center O of the circular coil due to the current element of length dl at point A is given by dv is equal to idl sine theta upon r square, the constant term mu naught by 4 pi. Here theta is equal to 90 degree, so dv is equal to mu naught by 4 pi ideal sine 90 upon r square. If we use the values, corresponding values, now we get dv is equal to mu naught by 4 pi ideal upon r square. This magnetic field given in equation 1 is at the center of the circle due to that elemental length dl only. Total magnetic field at the center is just the sum of such magnetic fields due to such elemental lengths dl throughout the circumference of the circle. So the total magnetic field is obtained by integrating equation 1 throughout the circumference of this circle. So let us see. B is total magnetic field is obtained by integrating that elemental flux density throughout the circumference of the circle. This is integration throughout the closed loop. Here the closed loop is the closed circle. Now we substitute the values of dv from equation 1, and since the constant terms can be made free of integration sign, we are writing this way. Now integration dl means adding dl throughout the circumference of the circle. That gives the circumference itself. So circumference is 2 pi r. Value of integration dl throughout the circumference of the circle is 2 pi r. That is the circumference itself. Now by simplifying, you get B is equal to mu naught I by 2r. This is the total magnetic field at the center O. If the circular coil has only one turn or a single turn, now if there are n turns of the coil, then we multiply the magnetic field due to single turn by the number of turns to get the expression for magnetic field due to circular coil having large number of turns. Remember this formula? You might use this formula to solve some of the numericals. Okay. Since the magnetic field is vector quantity, we must know the direction of magnetic field as well. The direction of magnetic field at the center O is perpendicularly out of the plane of paper